Hello everyone, and welcome to today's chem lesson. Today we're going to begin our discussion on solutions by first looking at pretty broad stroke definitions and looking at what it means when something actually dissolves. Right. First, we're talking about solutions, right? A new topic, a new concept. A solution, something that you've worked with pretty frequently, I'd say, throughout your life. When we look at a solution, we're looking at a homogeneous mixture made up of two or more substances combined in a single phase. And there's two pieces, right? These two pieces I pulled out that we want to address. It's been a while since we talked about mixtures. A homogeneous mixture is a mixture that is evenly distributed. Right, something where all of the parts are evenly mixed together. Right, that brings us here, right? It's a physical mixture and not a chemical reaction. A physical mixture means that I can undo and separate out the parts. And here, combined in a single phase. When I take something and mix it into a solution, right? When I take solute and put it into solvent, I get one phase out of this, right? Whether this is a solid going into a liquid going into a liquid, a gas going into a liquid, right? Any of those things will give you one phase at the end, right? It will give you a liquid solution for these examples we have here. So, is the solvent always a liquid? No. So actually, you can have a bunch of different things, right? You can have a gas going into a gas, you can have a liquid going into a gas, you can have a solid going into a liquid, right? You can have any combination of phases to make a solution. The solutions that we focus on, the things that are the most common, are going to be solid going into a liquid and liquid going into a liquid. Right, these are what we tended to do the most interactions with. Oil and water is not at all a solution, right? Oil and water doesn't mix. In order for this to become a solution, like I said, we need a mixture to be formed. Since oil and water don't mix, they don't actually interact with each other. Right? When I put my pen on a desk, I don't make a solution because those two things don't mix together. Now, along with solution being a new vocab word and this new concept, we're going to look at solute and solvent. The phrase that I always use to remember them is this: the solute is dissolved in the solvent. Right, so the solute goes into the solvent. Right, that means when I'm looking at an example like this, and I put my solid into my liquid is my solute, the liquid is my solvent, and when they are combined and mixed, I get a solution. Here, this drop of liquid goes into this other one to mix together, and so I have solute going into the solvent to make my solution. The most common solvent that we are going to look at is going to be water. Right? Almost all of the things we are going to look at is going to be putting something into water. Right? Whether that's putting a liquid or a solid or a gas into water, that's really our focus. And so we want to look at what it means when something dissolves in water. When I take salt, I take a spoonful of salt and I dump it into my water and I stir it up, I'm going to make some pasta. That salt dissolves. if I look at my container of water, I can't see the salt in there anymore. So what happens to that salt? Right, that salt dissolves. It gets hydrated. The water molecules pull apart the salt. It pulls apart the Na and the Cl, the sodium and the chlorine, and it surrounds them. And this means that when you look, right, if I have my eyes right here and I'm looking at this set of ions, all I can see is the water. I can no longer see the salt because it has been broken apart and surrounded by water molecules. The water molecules pull apart whatever is being dissolved, separate them from each other, right? Like a sugar cube, it's going to separate the sugar from the cube, slowly spreading it out throughout the water, surrounding those molecules, right? Surrounding those molecules, and then it will be dissolved. And this state that we have here, right, ions or molecules surrounded by water, is where our AQ, aqueous modifier, comes from. All right, when we talk about NaCl solid, we're talking about, obviously, the solid form of salt. But when I put that into water, I get NaCl AQ, the dissolved form of salt. Right, these ions have become hydrated, surrounded by water molecules, and dissolved. And if we look closely at these two diagrams here, you notice that the waters are facing opposite directions. For the chlorine, the oxygen is facing out, and the hydrogens are facing in. And when we look at the sodium, the oxygens are facing in, and the hydrogens are facing out. Now, what causes this? Why aren't they facing the same way? Why aren't the oxygens always facing in or always facing out? What's the difference between the sodium and the chlorine that might cause this flipping of the water molecules? Chlorine is a negative ion, and sodium is a positive ion. Now, why does that matter? If we think back to our discussion from a few units ago, we talked about polarity and how water is a very polar molecule. There is a surplus of electrons up here by the oxygen, because oxygen has such strong electronegativity that we get a sort of negative charge. And the deficit of electrons at these hydrogens gives us a sort of positive charge. And so taking the polarity of water in mind, when we look back at this, we've got a negative ion here with the chlorine, and the positive end of the water is attracted to it. On the other hand, we've got the positive ion in sodium, and the negative pieces of the water are attracted to that, right? Opposites attract. And water being polar is one of the most important reasons why things dissolve in it. Water's polarity of substances. It allows it to dissolve other polar substances. And when we look with closer detail here, Gotta redraw this water. When we look in closer detail, water pulls apart the ionic substances. Right? It will take an ion and pull it away from the molecule, right? From this big clump of ions, and surround that ion. It'll do the same for this positive ion. Over and over and over again, these water molecules are going to go, pull off an ion, separate it, surround it. Rinse and repeat until this whole thing has been dissolved. But it can only do this because of its polarity. Because water is polar, because it has these partial charges, it can interact with these charged ions. If these things weren't ions, if they had no charge, if they were just non-polar pieces sitting together, water can't pull this apart. There's nothing that gives water any strength to pull on this non-polar thing. Right? Water's ability to dissolve things comes from its polarity. That being said, what happens if this attraction between the positive and the negative in our substance is stronger than the attractions here? What happens if water isn't strong enough to pull this ion away? So every time we look at an ionic substance and we want to know if it dissolves in water, we need to ask ourselves, is water's polarity stronger than the attraction between the ions? Is water strong enough to pull this ion away from the others? If it is, right, if the answer here is yes, the substance will dissolve. If the answer is no, if water isn't strong enough to pull this ion away, the substance will not dissolve. It won't interact with the water. And as we move forward, next time when we look at Table F together, we are going to see how Table F answers this question for us. How we can use Table F to see if something will or will not dissolve, based on whether or not the attraction between the ions, right, this attraction, is stronger or weaker than these attractions that the water has with the ions. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.